Hello and welcome back. Today we will learn about reservoir simulation. Reservoir simulation is a very powerful reservoir management tool. It brings us a deep understanding of the reservoir and the ability to predict how it will behave in response to various development scenarios. Being able to predict reservoir behavior is very important as it will help us solve many problems that might arise at any stage of field development. Engineers of the past used physical and analog models long before computers, and today's software is so advanced that modern digital models can simulate reservoir behavior with incredible accuracy. In the mid-20th century, oil companies came to understanding the opportunities that mathematical modeling brought. However, back then technology was not that advanced, so modeling was used only for largest fields that could bring enough oil to justify the expenses related. It was mostly employed to obtain a production forecast that could be used for long-term development planning. Now that computers are everywhere, and their processing powers are amazing, we can build a model for a field of any size and use it for both planning and operational control. We shall start with geological modeling. If you want a simple definition, geological modeling is about representing the distribution of porosity and permeability within an oil field. A geological model also needs to account for reservoir heterogeneity, connections between various permeable bodies, and any obstacles to fluid flow. Modern geological model is a three-dimensional detailed image of the reservoir. From such a model, we can learn about reservoir structure, rock and fluid properties and distribution. We will then use it as a premise for building a reservoir model which will simulate flow of fluids in the reservoir. Geological model also accounts for uncertainties that are unavoidable if we want to build a realistic model of an existing geological setting. Each stage of field exploration is associated with uncertainty. Direct information on the reservoir is available only from cores, which unfortunately represents a very small volume of rock. Just imagine, a typical geological model is built of cells or blocks 50 by 50 meters in area and half a meter in height. Any data that we will obtain from core analysis will represent only a tiny part of it. If so, how can we know anything about remaining mass of rock? We cannot. We can only make guesses about depositional environment based on core data, analog outcrop study, and indirect data that comes from seismic survey, well testing, and logs, which is often vague and controversial. So, before we start building any model, we need to gather and prepare data, including data quality and consistency analysis. For example, we need to check where or what a contact is according to various logs and check these values against well testing results. There are 5 basic steps to building a model. First, you build a structure, measure formations and faults. Then, you correlate formations from well to well. Then, you build a grid. You decide how many cells will be in your model, how large they are going to be, and how they will be arranged. After that, your model features areas with similar properties distribution. And finally, you describe petrophysical properties. Each cell will have its own value of porosity, horizontal and vertical permeability, saturation, etc. After our geological model is ready, we need to convert it into a reservoir model. This is done via a special procedure called upscaling. But do we really need to do it? Why cannot we just use our geological model as it is? I already told you that a typical geological model cell size is 50 by 50 by half a meter. An average model contains millions of cells, a large one tens of millions. Modern workstations are powerful, but not powerful enough to handle a multi-million cells reservoir model, especially if you want to have the results within reasonable time. So we need to reduce a number of cells down to, say, several 100,000. We need to go from fine grid to a coarser one, that is, to upscale the model. Upscaling is done in 2 steps. The first step is upgrading, that is, combining fine grid cells into coarser one. Cells are combined based on similarity of certain properties. There are various automated methods implemented in modern commercial simulation software. The second step is upscaling itself, that is, transferring cell properties from a fine grid to a coarser one. Upscaling of such properties as porosity, saturation, or net-to-gross ratio is relatively easy. It is done with help of averaging methods. Upscaling permeability, that is a real pain in the neck. There are lots of articles and books dedicated to this problem. There exist multiple numeric methods, many of which are incorporated in commercial software as well. What will happen if you don't upscale permeability? Due to numeric dispersion, water in the model will flow faster, which will cause early water breakthrough, and the overall situation will be very far from real life, so the model will be totally unreliable. That is why we need to upscale permeabilities, resulting pseudo-permeability curves will represent fluid flow through our larger cells very similar to the way it would flow through many smaller cells. After the upscaling, we end up with the so-called reservoir model, a digital reservoir through which a digital fluid will move just like the real fluid will flow through the real rock 2 or 3 kilometers below the Earth's surface. Reservoir simulation is an essential part of modern petroleum engineering. In my country, authorities will not allow the company to develop an oil or gas field without building a reliable reservoir model first. Numerous simulation software packages are commercially available today. Although they are different, they serve the same purpose. Modern reservoir simulation is a complex process. Before we even start building a model, we need to go through several steps. The first one is a problem statement. What is the purpose? What information is required? At this stage, we gather as much data about our reservoir as possible and determine which deliverables we will need and how soon. Then comes initial data analysis and processing. All the information we have gathered needs to be transformed to the required format. Any gaps and inconsistencies in the data need to be removed, and we have to decide whether we have sufficient information and whether it is accurate enough to build a reliable model. After that, we choose model type and will depend on our purposes. For example, there are cases that we don't have to model the whole reservoir. And then we build the model itself with as many cells and as much complexity as required for the task at hand and allowed by the time and resources available. Okay, we have finally built the model. How can we be sure that it is reliable? If we have historical data for the field we have modeled, we want to try and reproduce this history with our model. If calculated values of pressures and saturation will fit in with actual historical values, our model is considered reliable. If not, we modify cell properties and run the model again. This process is called history matching. After the model has been history matched, we can use it for our purposes. That is to predict how reservoir will behave under various development scenarios. One of the most complicated aspects of prediction is to evaluate the results, as they can be represented as thousands of text strings, and we need to pick out those that are required for our purposes. The final stage is preparing a report. Reports can take various forms, from a short memo to many volumes of text supported by multiple charts. The deliverables that we'll come up with are of 2 types. First comes general information, including such data as oil, gas, and water production rates, water home pressure, etc. They may be shown for the whole field and for separate wells. Usually, this type of information is represented as time-based charts. The second type of deliverables is spatial distribution of properties such as saturation and pressure at each time step of the simulation run. This information is usually coded as binary files that can be opened using spatial software. By now, you certainly understand that complicated and important job simulation engineers do. Using a reservoir model, you can estimate the distribution of remaining recoverable reserves in real time and evaluate efficiency of well simulation jobs. You can see calculation results in a very graphic and comprehensible form and make prompt decisions on how you want to operate a certain well further on. You can compare various scenarios, for example, hydraulic fracturing, in-field drilling, or site tracking, against your base case scenario. That is, scenario when you keep on producing a certain well as it is. You can evaluate risks associated with various simulation jobs, such as drilling in flush zones or hydraulic fracturing in bottom water-drive reservoirs. However, doing so requires a significant level of detalization and sophistication, so you need to be very careful with your data. This is all about modeling. See you next week.